Hello and welcome to this video. In this video, we will further study 10 more problems on polynomials and theory of equations. We have covered up to problem number 70 and now we will cover from problem 71 to 80. So let me put this in full screen mode and the other one also. Okay. So as always, I will say that when I am reading the problem, you should pause the video and try to solve the problem yourself. If you cannot solve the problem yourself, you should look at the solution. The other instance when you should look at the solution is when you want to match the answer. Now, without further ado, let's get started. Question 71 says that if D, E, F are in GP and the two quadratic equations ax square plus 2bx plus c is equal to 0 and dx square plus 2ex plus f is equal to 0 have a common root, then prove that d by a, comma, e by b, comma, f by c are in HP. So we are given that d, e, f are in GP. So immediately we arrive at df is equal to e square. Now if you look at discriminant of the second equation, that is d is equal to 4e square minus 4fd. And we have fd is equal to e square. So we substitute it, we get 4e square minus 4e square is equal to 0. Now discriminant being 0 means the second equation will have only one root, which is the repeated root, which is equal to minus 2e by 2d, which is equal to minus e by d, which is the common root with the first equation. So we substitute x is equal to minus e by d in the first equation. And upon evaluation, as you can see, we arrive at the fact that a by d plus c by f is equal to 2be by df. Now df is nothing but e, which is equal to 2b by e. So if you look at this relation, a by d plus c by f is equal to 2b by e, means that a by d, b by e and c by f are in AP, and therefore d by a, e by b and f by c are in HP. Question 72 says that if n is even and alpha beta are the roots of the equation x square plus px plus q is equal to 0, and also of the equation x to the power 2n plus p to the power n x to the power n plus q to the power n is equal to 0, and fx is equal to 1 plus x to the power n whole to the power n divided by 1 plus x to the power n, where alpha to the power n plus beta to the power n is not equal to 0, p is not equal to 0, this is equal to is wrong, p is not equal to 0, and find the value of f of alpha by beta. So we look at problem 72. We are given that x square plus px plus q have two roots, alpha and beta. So alpha plus beta is minus p and alpha beta is equal to q. Now, if you look at the solution, here there is something wrong. So alpha and beta are roots of this equation as well. So we are given this should be x square to the power n and this is x to the power n. So we can write that alpha to the power n plus beta to the power n is equal to minus p to the power n, and alpha to the power n beta to the power n is equal to q to the power n. Now f of alpha beta is equal to, if we substitute x is equal to alpha by beta, we get alpha plus beta whole to the power n divided by alpha to the power n plus beta to the power n. Now alpha plus beta to the power n is minus p to the power n, and alpha n plus beta to the power n is minus p to the power n, and which is equal to minus 1. Question 73 says that factorize x to the power 4 plus 4 as product of irreducible polynomials over the sets q, r and c. So we have over q, x to the power 4 plus 4 is x to the power 4 plus 4x square minus 4x square plus 4, which is equal to x square plus 2 whole square minus 2x whole square. So these two and this term when combined, it gives us x square plus 2 whole square and minus 4x square is 2x whole square, which is equal to x square plus 2x plus 2 into x square minus 2x plus 2. So over R also this is said. Now over set of complex number, we will have to further factorize these two equations. Okay. So this equation we add and subtract minus 2x. So from this equation, we have x is equal to minus 1 plus minus I, and x square minus 2x plus 2 will give us x is equal to 1 plus minus I. Therefore, x square plus x to the power 4 plus 4 over c, when we uh, factor it into irreducible polynomials, becomes equal to x plus 1 minus I into x plus 1 plus I into x minus 1 minus I into x minus 1 plus I. Question 74 says that check if x to the power 4 plus x to the power 3 minus x minus 1 is irreducible over z. Now we have x to the power 4 plus x cube minus x minus 1. So from first two terms we take x cube common, it becomes equal to x to the power 3 minus 1 into x plus 1, which is equal to x minus 1 into x plus 1 into x square plus x plus 1, and therefore it is reducible over z. Question 75 says that check if x cube plus x square plus 3 plus x plus 3 is irreducible over z. So it is a cubic polynomial. So if this is reducible, then it would have to have a linear factor x minus alpha. And so, hence we will have a root alpha in z. But by integer root theorem, which we have studied, alpha would have been an integer divisor of the constant 3. That is this. But so it would have to be 1 minus 1, 3 or minus 3. So this alpha root, one of the roots factors, that is root or factor, can be 1 minus 1, 3 or minus 3. However, if you substitute these and try to divide, you will find that none of these are a root of the given equation, and therefore the polynomial is irreducible. Question 76 says that show that x to the power 4 plus x cube minus x plus 1 is irreducible over z. So following like previous problem, we use integer root theorem and we find that we have no integral roots and therefore no linear factors. However, it might be product of two quadratic equations. So we consider that it is product of two quadratic equation x square plus ax plus b and x square plus cx plus d. So now we equate the coefficients. We find a plus c is equal to 1, b plus ac plus d is equal to 0, ad plus bc is equal to minus 1 and bd is equal to 1. Since a, b, c, d are all integers, we have either b is equal to d is equal to 1 or b is equal to d is equal to minus 1 from this equation. In the first case, that is b is equal to d is equal to 1, the other equation becomes a plus c is equal to 1 and ac becomes equal to minus 2 and a plus c is equal to minus 1, which is impossible because a plus c cannot be 0 and equal to minus 1 at the same time. Okay, which is impossible. And in the second case, when b is equal to d is equal to minus 1, we have a plus c is equal to 1 and ac is equal to 2, which has no integer solutions. And therefore, we cannot factorize it and polynomial is irreducible. Question 77 says that prove that if the integer a is not divisible by 5, then fx is equal to x to the power 5 minus x plus a cannot be factored as a product of two non-constant polynomials with integer coefficients. So we suppose that it can be factored. Okay, so f of x is equal to x to the power minus of into g of x. Now fx is equal to x square minus bx plus c into gx. So there are two possible cases here. Okay, so in the first case, f of n is equal to n to the power 5 minus n plus a. Now n to the power 5 is equivalent to n mod 5 from Fermat's little theorem. Now 5 is divisible by b minus b to the power 5 is equal to a, which is a contradiction. In the second case, f of x is equal to x to the power 5 minus x plus a by x square minus bx plus c. We get the remainder, we divide it by that. We get the remainder b to the power 4 plus 3b square c plus c square minus 1 into b cube c plus 2b c square plus a. Since x square minus bx plus c is a factor of fx, both coefficients of remainder equal to 0. And therefore, b to the power 4 plus 3b square x plus c square is equal minus 1 is equal to 0. And b cube c plus 2b c square plus a is equal to 0. Which means that b into b to the power 4 plus 3b square x plus c square minus 1 is equal to 0. not 0, minus 3b cube c plus 2bc square plus a is equal to b to the power 5 minus b minus 5bc square minus 3a is equal to 0. That is 3a is equal to b to the power 5 minus b minus 5bc square, which means that which is divisible by 5. It means that 5 is divisible by a, which is a contradiction, and therefore uh, our proof is complete. Question 78 says that let fx is equal to a to the power n x to the power n plus an minus 1 x to the power n minus 1 plus so on up to a1x plus a0 be a polynomial with integer coefficient such that a0 is a prime and mod a0 is a prime and mod a0 greater than mod a1 plus mod a2 plus so on up to mod a, and prove that fx is irreducible over z. So 78, we say that here let alpha be any complex 0 of f. Okay. Now the first case could be that mod of alpha is less than 1, less than or equal to 1. So if mod of alpha is less than or equal to 1, then we have mod of a0 is equal to a1 alpha plus a2 alpha square and so on up to an alpha to the power n, which is less than or equal to mod a1 plus mod a2 and up to mod n, which is a contradiction. Now since we have proved this case, therefore all the zeros of f must satisfy the condition mod alpha greater than 1. Let us assume that f of x is equal to g of x into h of x, where g and h are non-constant integer polynomials. Then a0 is equal to f0, because if we put x is equal to 0, only a0 will remain, which will be equal to g0 into h0. Since a0 is a prime, mod of g0 comma h0 equals 1. Okay, so that effectively implies that h0 cannot be split into two parts. Okay, that means one of the g or h should contain a0 and the other should contain 1. So we assume that mod of g0 is 1, then and also let b be the leading coefficient of g. Now we let alpha 1, alpha 2 up to alpha k are the roots of g, then mod of alpha 1, alpha 2, alpha k is equal to 1 by b. So in this case, leading coefficient of the g is supposed to be b here. So it can be any power between n minus 1 to 1. Okay. Now from that, b, since b is the leading coefficient and alpha 1, alpha 2, alpha k are the roots of the coefficient, so mod of product of roots is equal to 1 by mod b, less than is equal to 1, because the b is in set of what you call complex numbers, not complex number, z, I don't remember, I forgot this. Okay, so but alpha 1, alpha 2, alpha k are also zeros of f, and from case 1 we have have magnitude each greater than equal to 1. So that means mod of alpha 1, alpha 2, alpha k is greater than equal to 1. From this case we have, from case 1 we have this condition. So that means this will be greater than 1. Now here we have less than equal to 1, the mod of product of roots. So therefore this is a contradiction and therefore f is irreducible. Question 79 says that prove that 16x cube minus 35x square plus 105x plus 175 is irreducible over z. So the given polynomial is irreducible by Eisenstein's criteria, with 7 being the prime p. So here the prime p of the Eisenstein's irreducible criteria, let's revisit that and it will be clear. This is problem number 79. Okay. So I will quickly revisit the Eisenstein's criteria for this, because this is a new problem. So what we have here is, this is our fx with integer coefficient if there exists a prime p such that following three conditions apply. P divides each ai. Okay, p does not divide an and p square does not divide a0. That is the Eisenstein's irreducibility criteria. So from 0 to n it divides. P divides, that is P divides A0, but P square does not divide A0 and P does not divide AN. That was the criteria. So just to refresh that, now we are on problem number 79. Okay. So if we see this polynomial which we have, okay, our P is 7. So 7 divides this, but 7 square does not divide 175, and 7 divides these two as well. So our P is 7, and 7 does not divide the leading coefficient. 16 it does not divide, and therefore from Eisenstein's criteria, uh, it is irreducible. Okay. But if we, the other possibility of picking a prime is 5. Okay. But in this case, the problem is 5 square will divide 175. So it will not work. Okay. Now question 80 says that prove that x cube to the power 3 minus 3x square plus 3x plus 22 is irreducible over z. So here we cannot apply Eisenstein's criteria because there is no suitable prime. So these two are not divisible by 2 but 3. So these two are divisible by 3, but 22 is not divisible by 3. So what we do is we substitute x minus 1 for x in the given polynomial, which gives us x to the power 3 minus 6x square plus 6x plus 21. Now if you see, these three terms are divisible by 3, but 3 square does not divide 21. So Eisenstein criteria can be applied here. So we find that x minus 1 is irreducible. But if you factorize fx, it will give you a factorization of fx minus 1, and therefore fx is irreducible over z. So I hope that you have found these 10 problems useful and informative. So let me know what you think about these videos, and I'll wait for your comments. Make use of the comment box. Thanks a lot for watching the video. Bye.